All right, let's start on time. Today, we're going to cover quite a few interesting topics. We're going to wrap up our discussion on virtual memory. We'll take a closer look at how our processor handles the page fault, okay? One important concept that we covered last time. We also introduced the concept of exceptions and interrupts. Actually, page fault is one of the exceptions. And also we'll look at how our computer system incorporate input and output devices. We usually call them I/O devices. Right. As usual, I have a few announcements that foresee is that the last portion of our lab is due tomorrow. And after you guys are done with the lab, please take a look at the announcement that I already made on Piazza. Right. So there's a link to a Google form. So that's where you can find the logistics, right, for the FPGA board return. Again, take a closer look at that post and also the form. Not everyone needs to fill out the form, but if you do need to fill out the form, please do so by Sunday this week. Right. So one of our EC staff members will also follow up with you. And we do need everyone to return the board by 28th. Okay. So if you're on campus, things will be much easier. All you need to do is to go to Phillips Hall, I believe, and then return the board. Okay, and a bit more about final exam. Already mentioned last time that this is going to happen right on Sunday, 23rd. It's going to be, so the exam will have 110 minutes. I'll give you guys more details on Thursday. Okay, we'll also announce review session, office hours for the final week, the study period, pretty soon on Piazza. The plan is also to host a sample final exam this week. Okay, but one thing is, please do let me know in case you have a schedule conflict. Okay, so let's talk about let's come back to the technical topics. Right, so let's quickly review what we covered last time. We talked about virtual memory, right? So where all the addresses are virtual, right? The program sees virtual addresses. And the way that we translate the virtual address to physical address is by using this so-called page table, right? And inside the page table, we have this so-called page table entries, PTEs, right? We use this VPN or virtual page number to address the page table. And if we have valid page table entry or valid PTE, we can retrieve, right, the PPN or physical page number. And then we just concatenate this page number, physical page number with the page offset, right? That's how we get the physical address. Okay, and usually for the modern system, also in our case, each page has 4 kilobytes, right? Which is 4096 in decimal. This is a quiz that you guys did, right? I'm asking you guys to figure out how many potential page fault that we have, and this is a page table. Right? Again, the assumption here is that this is the very first PTE or PT0, right? And this is the second one. So to solve this quiz, all you guys need to figure out is the VPN, right? The virtual page number. For the first one, obviously this is in the very first page, right? Which is VPN 0. And the second one, same thing, right? The first one will incur a page fault, right? Since initially the valid bit over here for this page table entry is 0. That's where we bring in the page from disk. But in the second, right, for the second access, so this is where we'll no longer have a page fault because the OS in the hardware has already allocated the physical page. Okay. And this one, right, is valid, so this is not a page fault. And same reasoning here, right? Even though the VPN 0, but it's already in the physical memory, right? So basically the correct number of page fault is 1 in this case. Any questions about this one? Okay. If not, let's talk about this address translation a bit more. At the end of the last lecture, I actually pointed out the one performance issue, right? There seems to be a performance bug with our system. Now that we have introduced this virtual memory, we have to look at the virtual address, right? And we have to go to the main memory to find the page table and translate the virtual address to the physical address. But that's sort of defeating the purpose of using cache. Right? We introduce cache in SRAM to speed up the this memory access. But if we have to go to the page table before we get the physical address, that seems to be super slow, right? I remember that at the end of the last lecture, one of you already suggested the solution. Okay? In this case, we really don't want to go to the main memory all the time, right? So that's just not gonna work. Can we cache? So the thing is, this page table access also have good locality. Right? We access a whole page at a time. Can we also cache the most recently used PTEs within the processor, within the processor pipeline? So that's the main idea. And this cache is called TLB, translation leukocyte buffer. Right. So there's actually one question in the homework, right? In the last homework 8, where we introduced this concept, TLB. The idea again is pretty straightforward, right? All we want to do is we want to introduce a cache for the page table. And in this cache, we look at the data block, right? In this cache, this data block holds the physical page number. So this is the data block. And the tag we used to address this cache for TLB is the VPN, the virtual page number. Okay. And we usually just use a fully associated cache in this case, since we really want to minimize the number of misses. We really don't want to go to the main memory, right, for the address translation. This is crucial for us to get high performance. Usually for TLB, we have roughly 16, right? This is the rough range, 16 to 512 entries, again, fully associative. Okay. No surprises here, right? Valid bit, we need a valid bit. What about this reference bit? Anyone remembers? Why do we need the reference bit? What's the use of the reference bit in this TLB? And also same thing, right? We have a reference bit in the page table for each PTE. Very good, right? For LRU replacement, although this is not the exact, not the precise LRU anymore, right? We are just using approximate LRU. If reference bit is 1, that means this page, the corresponding page, has been recently accessed, okay, in the last refresh window when we refresh the page table and also TLB. How about 30-bit? 30-bit means what? Means that are we doing write through or write back? Guys, if a 30-bit, okay, 30-bit means write back, right? Because we want to keep track of the inconsistency between the, right, the cache and the main memory for the actual physical cache. In this case, we want to keep track of inconsistency between the main memory and the disk. All right, any questions about TLB? The concept is fairly straightforward, I hope, right? The key thing is, once again, we use the VPN, right, the virtual page number, to address a fully associated cache. We do need to search all of them, right? Since this is a small cache, all of these entries in parallel. Okay. Right, so just want to further elaborate a bit, right, how we actually use TLB. So when there is a TLB miss, what does that mean, right? There are actually 2 scenarios. If you miss a TLB, first, we need to go to the main memory to find the page table, right? How do we find the page table, guys? So there's actually a special register. Do you guys still remember? There's a special register called PTR. What's the full name for this thing? PTR. We use that special CPU register to find the page table in the main memory. Page table register, very good. That's basically host address of the very first PTE. Okay, we find the page table, and in case there's a hit, we just update the TLB. Okay, this can be done in hardware completely. Otherwise, if you have a TLB miss, and we also have a page table miss, that means a page fault. This is actually one kind of exception that I'm going to introduce, page fault, which means we actually need to allocate the page in the physical main memory, and this is where we need help from OS, operating system. We need to bring in the page from the disk. We also need to update the page table and the TLB. This is actually very costly because we have to interact with the disk. This can be very, very slow. Okay, if you're using an old kind of disk, even with the new disk like SSD, this is still much slower than accessing DRAM, the main memory. Okay, this is TLB, right? And of course, once everything is updated, right? So that's where we can retry the access, and that's where we can quickly, in the ideal case, right? Also, hopefully, in the typical case, we will only need to access the TLB. We access TLB, and then we find the physical address, and then we access cache, right? So where we can find the actual data value. All right. But in this case, right? One more thing. In this case, when we do have a page fault, I want to quickly make a note. We will definitely miss in the cache as well, right? Because we haven't seen this this data before. This data was not even allocated in the main memory, so this is definitely going to be a cache miss. All right. Okay, so last time I gave you guys some intuition, right? Some analogy for the VN, virtual memory, and page table. For the last lecture, I was using this the binder, right, as the analogy. The book, right? The book, very good, Mitchell. Book is the virtual memory, and the binder is actually the physical memory, right? Okay, in case everything, so you guys are not even looking at the hard copy, right? In case you're just using your tablet and cell phone. So I actually want to point out that I can also find analogy, right, in the thing that you are using pretty much every minute these days. Okay, so this is what you saw, right, in your smartphone, right? What is the page table over here? What is the page table? What is this thing, right? What is this thing? Right, very good. The contact list is actually the page table, right? If you look at this one of the entries, right, in this contact list, this is what? This is PTE, right? This is a page table entry. Okay. Right, Ethan is already ahead of the game, right? This is something that I want to ask next. Right? Where's TLB? Where's TLB? Ethan already gave his answer. Right. First contact is the page table, right? And we are also, you guys are actually using TLB every day as well, which is the reason, right? This, if you look at the recent context, this is really the TLB. Okay, and of course, right, favorite has sort of similar function, right? It's also a shortcut, but really, if you look at recent, right? So that's a more precise analogy. Okay, and I also want to point out, indeed, right? So this is a virtual memory because you guys really don't really want to remember the phone, right? The actual phone number of your friends. You only need to enter you only want to enter the name, right? Which is VPN. But this is VPN, right? VPN, and this is PPN. Okay. All right. Hopefully, this analogy will give you guys much better intuition behind why we are using TLB. Really, this TLB is a cache for an address book. That's it, a cache for faster address translation. All right. Okay. So let's move on. We've been talking about page fault, right? Actually, page fault is one kind of exceptions, as I alluded to early on. But what exactly is an exception? So this is where I want to introduce two concepts. One is called exceptions. The other one is called interrupt. These two are actually closely related to each other. These two are sort of the events, okay, that happen not too often, according to the perspective of the CPU. Okay, basically these are sort of the rare event, but this event must be handled somehow, right? When they occur. If this kind of event happen inside the processor, it's called an exception. If this kind of event happen outside the processor, okay, happens in a, let's say, I/O input-output device. This is called an interrupt. Okay, so these are the two right, kind of rare events that we want to pay attention to. First, again, these things, right, exceptions and interrupt, they are indeed very useful. So these are the useful methods for us to signal the CPU that some interesting event has occurred, and that requires a CPU to take some action. In response, the CPU usually suspend. Okay, suspend. This is an important keyword. Suspend the current running program, and then handle this exception and interrupt. Okay. So like I just mentioned, exceptions are used to handle the conditions or this kind of events that happen inside the processor when we execute instructions. This is detected by the processor itself. And the interrupts, right? So this is a very sort of an intuitive name, right? Interrupts. So something that interrupts the execution of the CPU. So interrupts are used to handle the external, usually asynchronous events, right, that happen outside the processor. Okay, so for now, let's just try to remember the distinction, right, and the rough definition of these two concepts, right? Events, right? These are rare events, right? And the internal one are called exceptions, and the external ones are called interrupts. Okay. So first, let's just take a closer look at the exceptions. I'll give you guys some examples of the interrupts later on. For these exceptions, again, these are very useful. This allows us to get service from the OS. For example, a system call, like when you try to print on the screen, that's actually a system call. Not all the program has the privilege to print on the screen. So you actually need to get permission from the OS. You need to get service from the OS. That's usually will incur an exception. And that's where the CPU and also the OS will kick out the current user program and transfer the control to something called exception handler. This is another new term that I need you guys to remember. Okay, we also talk about some analogy. We'll try to come up with analogy for this one as well later on. This is something that will do some pre-processing and then find the proper OS service. Okay. And these are some of the unexpected events. Okay, these are exceptions. For example, the memory protection violation. This is not something that I elaborated too much, but actually there's also another bit in the page table which indicates whether you are running in the privileged mode or a non-privileged mode. For a regular user program, we usually run in the non-privileged mode, but for OS, this is also a program, right? It's running on privileged mode. Okay, in case OS can actually access additional memory space, okay, which the regular program cannot access. It's usually called kernel memory. But in case a user program try to access the OS memory space, the kernel memory, that will trigger some kind of a memory protection violation. And also when one program try to access the space, right, from another user program, may also trigger protection violation. That's an exception. And divide by 0, when we do arithmetic, right, this is also an exception. In some cases, right, the program may be corrupted, right? We may have an invalid opcode. So that's where the processor may also trigger an exception. And one important exception is page fault. Okay. So this is where we execute the load and store instructions, or when we try to access instruction where it's not really in the instruction cache, right? It's not in the physical memory. So that's where we will need to deal with page fault. Okay. So this is something that we want to focus on this lecture, page fault. All right. So far, all of these are sort of dry definitions, right? But the important concepts are, right, exception handler, and page fault, right? Page fault is an exception. So let's just take a closer look at our pipeline, right? So now we need to handle these so-called exceptions. We actually need to extend our pipeline a bit. So first, we want to feed a signal, right, to the CU. This is a strobe, right? Exception. It indicates that there's some exception that's being triggered, right? And also we need to handle the exception, right? So that's where we need some additional registers. One is called exception PC. This is the PC of the instruction that triggers the exception, and also the cause, basically what kind of exception, the type, what kind of exception that we are dealing with. So this is something that we need to save. Then we handle the exception. And also pay attention to this part. So we also have another address, another instruction address. This is a PC of the exception handler. So we may need to load in the exception handler when the exception does occur. Okay, so these are some of the things that we have to add, right, to the processor. And also one more thing, right? You guys remember the previous diagram, right? So these two are also new. Right? We are also adding instruction TLB and data TLB into our pipeline for a good reason. Okay. There's a good question by Alma. The unexpected event could be the programmer's fault, but the page fault isn't, right? Yes, very good point. Okay, so some exceptions, for example, divide by 0 can be triggered by the programmer, right? And some of those can be triggered by basically how the memory is organized. That's why we need this so-called exception handler, right? That's why we need something to process, right? To classify different kind of exceptions. The exception handler will look at the cause, right? We'll look at the cause of the exception. If this is just something that triggered by the programmer, maybe the whole thing will just exit. The whole program will just exit. But if it's a page fault, right? So that's where we need to bring in OS. Right? We need to bring in help to handle the page fault. Okay, of course, these days, some of the programming language also allow you to add exception handler in your program, but that's a separate thing. Okay, that we are not going to cover in this class. Okay, so these are the extensions that we have to make to the pipeline, right? And this is the steps, right? I'm just going to quickly go over this, and I'll show you an example where things will be much more interesting and also much more clear. So with this exception handling, we need to send an exception signal to the control unit, CU, and CU will set the exception PC, so which is the address of the faulting instruction. What do I mean by faulting instruction? It is the instruction that causes the exception. Okay, so that's why it's called the exception PC. And all the instruction before this faulting instruction, we will need to complete. And then the faulting instruction, the one that causes the exception, and anything behind the pipeline will be turned into no ops. Okay, they'll be squashed. And we want to bring in the instruction inside the first instruction in the exception handler. So this exception handler is also a program. Okay? It's basically a special piece of a system software. Right? It's also a program which also contains a list of instructions. We basically want to bring in we want to run the program of this exception handler. Okay. And also after the exception is handled, we need to restart, right? We need to restart the program. For example, page fault, after page fault is handled, we want to restart the program that triggers the page fault. So that's where we actually need some mechanism. I'll actually turn this into a small quiz later on. We'll define this something called program state. We need to stop the program, suspend the program, we need to save the state of the program into the memory somewhere. Okay, so that we can later on resume this same program after the exception is handled. Okay, this is something that we're going to discuss later. Okay, all right. So these are the sort of the laundry list of things that we have to do, right? I'm just listing this for your reference later on, right? So if later on you're not too clear about some of what's going on in some of the examples, right? Go back to this list, right? And this is so you know exactly what's going to happen at which step. All right, so let's try to look at a concrete example. Over here we have a pipeline, right, which can handle exceptions. And we assume that we already have some instructions in the pipeline. And this specific instruction, this one, the sub instruction, is not in the main memory yet. The instruction itself, the instruction itself is not loaded yet in the main memory. What does this mean? Is it going to trigger TLB miss, guys? Yes or no? The instruction is not in the main memory yet. Yes. Obviously, TLB will miss in the TLB. After TLB miss, where do we go? We go to the page table. Are we going to find this instruction, the page of this instruction, the physical page number of this instruction in the page table? Yes or no? No, right? No way, because it's not even in the page table, right? Because it's not even allocated. It's not in the main memory yet. All right, so but what's going to happen is, right, the pipeline will execute whatever is before the sub instruction. Okay, the load and add, the add instruction will be completed by the pipeline. Right, the pipeline will stall and try to access the page table. Of course, this is also not a useful attempt, right? Because it's not even in the main memory. So that's where we have a page fault, right? This is where page fault happens. So let's see how the pipeline will react to this page fault. First, this is an exception, right? We need to assert an exception to the CU. And we also need to put the PC, okay? So basically the address, read the address, this address of the sub instruction, subtraction instruction to the exception PC. And we say that the exception cause, right? This is basically a type of exception, is page fault. We update these two registers, right? This one is another write enable. Okay, this is a write enable. This is an exception load. EL means exception load. We just set it to 1. Right, when we update these two registers. Okay. After that, what do we do? That's where we need to bring in the exception handler. Okay. So we'll let exception handler take care of the rest, because the program itself, right? The specific program itself cannot load from the disk, cannot load data from the disk. This is where we need help from the OS. Okay, then we execute the very first instruction in the exception handler. Okay, does it make sense? So this is the sequence. Right? We actually need to bring in another program to handle the page fault. Right? It's not like this program will magically happen somewhere else. We are assuming that we have a single microprocessor over here, and this program also needs to be executed, including OS, right? Also needs to be executed on this microprocessor on the very same pipeline. It's just that we have to somehow suspend the execution of the previous program and to save the state somewhere. Okay. All right. So let's take let's just do a quick recap right, of what's just what I just showed you. Okay. First, we are looking at this sequence of instruction. Right. You have add, load, sub, and somehow there's a page fault for sub. There's no page fault for add and LW and load. What does that mean? Let's say add has a address of X, right? And then load in our 2300 microprocessor, the load has an address of X plus 2, right? These are all virtual addresses. Okay. And what else? What about the next one? What does it mean? Right, this one X plus 4, right? Of course. But these are the virtual addresses. If you look at the corresponding VPN, let's say these instructions, right? These two, they are on VPN. Okay, this one has VPN, let's say N. What about the sub instruction? Can you guys, based on the behavior of the pipeline, can you guys tell me what is the VPN of the sub instruction? Has to be n plus 1. Make sense? Great. This sub instruction has to be on a different page, a different virtual page. Right? Because add and load, right? They did not trigger page fault. That means, you know, the corresponding physical page, they are already loaded in the main memory. But for the sub instruction, this one must start a new page. Right? Which means that we are actually looking at a page boundary, right, between the load and sub. Is it clear? Okay, this is somewhat interesting, right? Okay, that's where we have a page fault, and we have TLB miss, page table miss, and CPU generates this page fault exception. Then the exception handler steps in, will save the program state, and then transfer the control to the OS. Okay, then OS will be hard at work. OS will bring in the pages, update the page table and TLB, and restore the program state and resume the program. Okay, so you know this is something that OS can do. All right, is this sequence making sense? Any questions? All right, good. Looks like pretty good so far, right? And after that, we can resume, right? We can start executing the same program again, this program again. We can do this up. All right. How are VPN calculated? Yeah, Amanda, this is a good question. So VPN is just a part of the address, right? Remember now that our program only sees the virtual address, right? We have something called page offset, right? And then we have VPN. I keep writing VN because I was writing another paper the other day where we had to destroy VN. VPN, okay, VPN. Right, so basically this is part of the address, VPN. And how many bits do we have? Just want to remind you guys, how many bits do we have for the page offset? We have 4 KB, right? Per page, we have 12 bits, right? And the rest, they are just VPN. Okay, Ambrose asking, is the OS bringing in the page faster? What do you mean by faster? It's not that it's faster, it's just that, you know, we have to rely on system software to handle the main memory, right? To update. We have this so-called virtual memory, right? So like I mentioned last time, it's a co-designed. This is really a co-designed solution where we need to rely on both hardware and OS. OS and hardware, they need to work together to update this main memory. The OS has the control, right, to bring in, to allocate new pages in the physical main memory. We cannot rely that. We cannot ask a regular program, right? For example, you know, one of your app to do that. That'll be very horrible, right? That could be catastrophic because remember last time we mentioned that, right? One app cannot interrupt, right? Cannot corrupt the memory of the other app. So these are something that we wanna, right, make sure. So there's a security aspect as well. OS is something that we can trust. We trust OS. OS basically manages all the resources. We trust OS to do the right thing with the main memory. All right, Amanda's also asking if there's a loop with some instruction in VPN1 and some in VPN2. Would this happen every iteration? Another good question, Alma. What do you think? And this is actually related to the quiz, right? That I asked you guys last time. Right. Once we bring in the page, we are going to keep it in there, right, in the main memory. So that's where we are making use of the leveraging, exploiting the temporal, also physical, the spatial locality. We're now going to have another page fault, right? The second time we access the same instruction. This is also how this paging works, right? You know, in most cases, the program will spend most of the time in certain loops, right? So that's where we can get away with just a small chunk of just a small number of pages allocated in the main memory in many cases. Does it make sense? Okay, so we're not gonna hit the page fault again. All right, so we just talked about exception handler, right? I just want to make sure that you guys have the intuition, right, of what exactly is this exception handler doing. Can you guys give me some analogy? Maybe this time I'll ask the class to give me some analogy. Have we seen this kind of exception handler in our day-to-day lives? What is that? Any ideas? Any suggestions? No? No, I can turn this into a bonus question. You prefer? Fire alarm, traffic accident, right? Ethan, Max, very good. These are sort of exceptions, right? Traffic accident and fire alarm, right? Very close. These are exceptions. Right. Alma, you are almost there. Okay. Maybe when we, right, I was saying maybe when you get injured and an ambulance comes. Okay. Very good. 911. Excellent. Okay. Excellent. Okay. 911. So I think both of you are hitting the same, or really talking about the same thing. What is that place where the ambulance will carry you to? You guys know? Hospital? Can we be more specific? Right, very good. ER. ER, right? This is basically an exception handler. Does it make sense? Right? Basically, when we have an exception, right? You know, when someone gets injured or someone gets sick, right? All of a sudden, right? It's a rare event, right? And it's happened at midnight, let's say, right? That's where the ambulance comes in, will take you to the ER, and a doctor in the ER. So they are sort of the, you know, the programs, right? In the exception handler. They will give you some diagnosis, and then they will refer you to the, right, later on. Of course, hopefully, you know, if they can treat you, that'd be great. And later on, they can refer you to some specialist, right? And the specialist really refers to the OS routine, some additional OS routine. Depending on the kind of, in this case, depending on the kind of units that you're dealing with, right? The ER doctor will refer you to the right kind of specialist. And for our exception handler, depending on whether we are dealing with a page fault or we are dealing with, you know, some other program triggered exceptions, then the right kind of OS routine will be triggered. So those are basically specialists. Does it make sense? Yeah, so I think many of you already got the right intuition. Okay. So let's